Okay, so yesterday we discussed the way to one way to calculate Gromov Witten invariance is by some kind of recursion relation, which use the WDVV. Right? So that's one way of doing that. Unfortunately, this is that. Well, I mean, of course, that method is too easy, right? So by now, everything can be which is interesting has been calculated. So nothing left for you, unfortunately. So well, actually, that's not completely true. You have to explore new problems. But anyway, in Gromov Witten theory, there are a few, very few tools to do a calculation. So one is to use associativity relation, which we discussed in Jun 0. But more powerful tools are localization and degeneration. So I will talk about localization today and hopefully go on to degeneration also today. So to do localization, I'll first have to tell you what the equivariant cohomology is. Has this been talked about in the school yet? Equivariant cohomology? It has. Oh, student seminar. So should I skip that? All right, so we are only going to talk about T, which means C star, or maybe somehow C star to certain power. To certain power, something like that. So let's just take T to be C star, and I'm going to define equivariant cohomology in the following way. So I will define ET to be C infinity divided by C star. Oh, so sorry. So this is not divided by C star. So this is C infinity subtract 0, and BT is defined to be this C infinity ET divided by T. And this, you can imagine this as P infinity. Or if you're very picky, you can infinity plus 1 and plus 1 here and become P infinity. Just make sure all the counts match.
Is C infinity the set of all arbitrary sequences of complex numbers without any?
Yeah. Okay, so I'm not very, I'm not going to be as rigorous as Professor Corti. So to differentiate everything, these are certainly not algebraic varieties. So I mean, to define this properly, to define everything properly, I have to use some kind of finite dimensional approximation, and I have to prove that everything is independent of finite dimensional approximation, etc. But what I write is something which would make sense if you do a finite dimensional approximation. These are not, well, C infinity just means it's some kind of weak approximation to, you take Cn and take n to be larger and larger. So it.
The topology is an open set is a cylinder.
Yeah. So what I'm saying is I take weak topology, not strong topology. So okay. So once you have this, and what's this for? This, well, I mean, these will form sort of a universal family of principal T bundle. So T bundle. So this ET will be some kind of contractible. So this is contractible. So a space, and which T acts freely. Right? I want this to be contractible space where T acts freely. And if you're in a stack world, that would be, well, if you allow stacks, that would mean I can take this contractible space to be a point, for example. That was in a contractible space. And you say, hey, the T doesn't act freely, but you can pretend to act freely, and BT will become point quotient by the torus. But anyway, so that's This is what I'm going to talk about. So I'll define xt to be the quotient by t if so given, sorry, so I should have said given t action on x. If I'm given a t action on x, so I can always form this space where, because t acts on x and t also acts on et, right? So this quotient actually makes sense. It's diagonal action. Does that make sense? So so this is, for example, if x itself is t, then this will be just the same as et. Or x, if x is t acts freely, then this will be topologically isomorphic to, well, because this is topologically isomorphic to point, it's contractible. If so, the only, so this is just, I want to say that so this is, I want to, so heuristically, as I said, this is a contractible space. Heuristically, I'm replacing replace x by homotopy equivalent space such that t acts freely, right? X cross et, well, et is basically topologically a point. And so if I do x cross et, I don't change anything about the topology of x. But then, you know, t acts on x, not necessarily freely. And so I replace that by sort of a equivalent space which t acts freely. So that is what I meant by this. For example, if x already has a free t action, this you can just, xt, you can just think of this as x quotient by t. But if not, I want to replace that with something which t acts freely. So I define my equivariant cohomology to be cohomology of this quotient. So this is sort of a homotopy quotient instead of a real quotient. So there are a lot of hand waving here, but that's, I think that's what I figure out probably is something which is easier to digest. So yes.
In the notes, it doesn't look like you're defining xt as a quotient. Is that?
Oh, when I said it's over t there, I really mean it's quotient. So.
Okay.
So yeah. So in the notes, this is sorry, denoted differently as x t e t. But what does this mean? That means that it actually means yeah. So what it means, well, if you really want to ask, why did you write this? Well, I really mean the associated x bundle of that. So you have this t bundle, right? And I want to do what do I mean by associated x bundle? For any principal bundle, I can associate with any fiber bundle, right? Where the fiber has this principal group, as a principal G bundle, I can always associate with, like if I have a G space or G object, I can always associate the associate bundle. That's what I meant. But you know, here I was trying to not to explain that, but you forced me. Anyway, so that is this is that. You change the fiber basically. All right, so so for example, if you have e.g., if you x is a point, certainly t acts on that trivially, so it's not freely. And so what do you have? What you have here is point. This is the same as you see, if I put point here, the quotient will be the same as xt will be the same as bt. BT is CP infinity, right? And CP infinity, as we know, has, say, this will be Z, and then with, did I wrote T? Oh, no, Z. CP infinity will be generated by one single element, which is hyperplane of the CP infinity. And well, I mean, in CPN you have a relation, but relation get higher and higher degree. If you take a weak limit to infinity, then it disappears. Okay, that's something simple. And then the reason we want to talk about equivariant cohomology is that we want to do localization. So what does the localization tells us? Oh yeah, I should have said this. So once I have this equivariant setting, I can define, can generalize all the concepts in this this concept to T equivariant setting. For example, if you have a vector bundle, which I denote by E, and if you have T action on this, then you can define similarly this if a T equivariant vector bundle, and this is in this way, so that T acts on E and T acts on X compatibly. That's okay, right? And so I can associate this, and therefore I can define the chain classes, T equivariant chain classes. Oh, no, wait, this. So it will be a class here, which will be in the equivariant class. So this will be in equivariant class of X. All right, so I think I said everything that you need to know about equivariant cohomology, at least for my lectures, and maybe also for most other lectures as well. So now we want to talk about localization. What can I say about localization? Well, localization is the following fact that if you so if you have, again, our setup is our T acts on X, right? And then so now you have, so now the fixed locus can be written as this joint union of Xj. Did I write Xj? Yeah, Xi or Xj. Oh, that's probably notation I need to change. Anyway, so Xj, so Xj, all smooth. So the fixed so first fact here is that if T acts on smooth X, the fixed locus will also be smooth. Okay, this is the first fact. And why is that true? Well, you have to study this a little bit. But if you study enough, then this, again, to quote Professor Corey, this will be more or less obvious. But it's after some thinking that will become more or less obvious. Anyway, so then you have this. So the localization formula tells us that if you have a class X on X, then I can write this as J summation integration only over Xj. And then so that's the localization formula. And what Davish was using is the fact that I told you, right? So the idea of virtual class is that, well, these modular space has a horrendous geometry. but the virtual class behave just like smooth objects. It is virtual class from a smooth, say, orbital. So the virtual localization just means if you put virtual everywhere, it's going to work. So, but that part I will not use, but I'm just saying that if you put virtual everywhere, and this still works, if you have a perfect abstraction theory, and your T action of that, and then you can do the same thing. But we're not going to use a virtual setting. So these things will. So what I'm saying here is also true. This will be a if this is only virtually smooth, then this will also be virtually smooth. Does that make sense? If this is virtually smooth only, and this is also virtually smooth. So again, just to explain what's going on in class. But this theorem can be sort of very slightly generalized to what I call, or other people call, correspondence or relative. So you can do this so relatively in the following sense that so if you have mu from x to y, and then if you have, now I realize why I use I here. Sorry, it's okay if you don't want to change, because I have used I on one side and j on the other side. So suppose xt is disjoint union of xi and y. So this is a T equivalent morphism. From now on, if Professor Cordy sits in the class, I will try to say morphism instead of maps. So this yt is the joint union of yj. And so certainly, well, these look like, if you look at this, it looks like, what did it say? It says that integration of this alpha against the fundamental class of x can be written as sort of a residue, sum of residues on every sum of residue on every fixed point locus, right? Each fixed point piece gives me some kind of residue integral, and I have them sum over. So if you have this, so certainly the fixed point has to map to a fixed point by definition of T equivalence, right? So fixed point will map to a fixed point, but sometimes the two fixed points can map to one fixed point, etc. But fixed point has to map to a fixed point, and one fixed point certainly cannot map to two fixed points. Well, one fixed point connected component cannot map to two disconnected components. So you have this sort of. So we can say the corresponding residue is saying that this kind of integral, if enter under this assumption, would be something like so. Suppose that the only fixed component on x. So maybe suppose xi is the only fixed component mapping to xj for a given j. So suppose I take one connected component here. Suppose there's only one mapped to that component. Okay, then you do have this correspondence residue in the way that I'm going to be where I write EI, this just means n xi in x. This will be means n yj in y. So I use I on this side, j on the other side. So this kind of residue, if you push forward to the other side, will be the same as the radial on the other side. So to do it so it will be probably easier to see in this kind of diagram like this. You have x to y, and this is your mu, and then you have this xi here, excuse me, to yj here. And this guy give a radial, and this guy give radial. What I'm saying here is, if you take alpha here, push forward, calculate radial here, it's the same as calculating radial here with this alpha and push forward and pull back there. So this I, this j. And I'm using mu, restriction of mu as mu self by abusing the notation. Okay. Questions? So this is what we're going to use. Then so now I will tell you a very easy computation about the small j function, but because I was instructed again to define the big J functions so that other people don't have to do it. And so that's what I'm going to do. Okay, so define. So big J function. So the big J function here is the following thing. It's using the notation we used yesterday. S is an element here. So this will be some, and I will only define this for projective space, but to generalize this to any x will be more or less obvious. So define this for degree and for n. I think I hope what I wrote down is correct. Again, I encourage you to find mistakes and send your feedback to me so that I will correct all the mistakes together in the weekend. Is sum over all d, sum over all n. So in this case, this q is your numerical variable. In this case, well, if I were to write this correctly, I would have to write d again, just like last time. I have to write line because I used to have q to a beta, where beta is a homology. It's your curve class. But then I'm ignoring that because I have only basically one line and one dimension. I'm just writing it like this. So what does this say? This says that I have this moduli space. So I have to define this properly. So X is projective space, and I have degree D, and I have evaluation 1 to X, which is projective space. So I'm taking this. So this comes from the first mark point, and others come from the second up to nth mark point. Right? So this is a cohomology class here. I'm pushing forward cohomology class here. So this lies in. And of course, I add all these variables. So these involve Q, and then you also involve Q. In fact, it's a sort of vector valued function of Q and S. So it's cohomology valued function in Q and S. In S and Q, but well, again, in the exercise, you will learn why the relation between So the function as function of Q and function of it's okay. And just like I will explain this notation here is that I'm using this as so this is also in, so it's a power series in Q and Z inverse. So what I mean by, so in fact, so for each fixed Q will be, well, anyway, so this Z inverse comes from the fact that I'm writing this. So why do I, oh, actually, maybe I can just do this. Do I use 2? Yeah, I use 2. I don't know why. But anyway, so that's, so what I mean by Z minus psi is just I do this as a power series expansion. So, and so this is psi 1, psi 1, etc. So that's become power series in Z inverse. So this is a big J function. So then you have this small J function which was talked about just then. And so if I am to say that what the small function is, a small J function is, I'm going to restrict myself to to a divisor direction. So instead of S to be in H upper star, I'm going to choose my S just to be in H2, H1. It's just like this one. It will be okay. Maybe I'll just remind you. I will write A1 just to remind you. I'm using the child degree of this. So that means this will be written as S1H. Well, sometimes it's by some convenience you can also, or you can put this as A less or equal to 1. That will be S0, 1 plus H. Either way will be okay. So if you restrict this, everything to this, then your J small can be written as exponential. So I remember I wrote this up. Sorry. So my indices all goes to a top. So this will be S1H over Z, and then 1 plus degree greater or equal to 1, Q to a D exponential DS1 EVD lower star of psi. So this has to be derived. So so here's the exercise. In fact, this exercise was sort of organized in the notes. In the earlier, to do that is to prove that J big, when you restrict yourself to S, it's only in A1 of P1, will be the same as J small. Again, if I make a mistake, you cannot prove it. That means I make a mistake, and let me know. So I'll correct the notes. They look a little bit different, right? So you have this funny exponential parameter, etc. That's sort of packed in the divisor axiom, which I did not have time to explain too much. Okay, so so this will be our small J function and big J function. So just because you heard about this today, I will say this remark is that this big J function satisfies the J function satisfies the differential equation that S mu J, same as I forgot plus minus T mu star is that right? I hope I so this is the equation the J function will satisfy. And if you only have this A1 direction, you will have to restrict this to. So J function is big, then you can differentiate in every direction. And if you J function is small, you can only differentiate along the divisor direction. That's something. I probably don't have time to prove this, but anyway. So my goal is to show you how to calculate the small J function of projective space. The goal.
Can you specify again what you have in the denominators for the J function?
Sorry?
What do you have in the denominators for the J function?
What do I have for the denominator?
Yeah, it's Z times Z minus.
For psi 1, psi 1 is a descendant. Right, psi 1 is, so we discussed descendants, right? So
No, I'm not talking
yeah.
about psi. You have Z times Z minus psi.
Yes. And you can just, this Z seems to be redundant, right? So why do I want to put this Z?
Yeah.
And other than that, I'm just keeping the Z here, just keep track of the power of psi.
Oh, it's good. And the same of the.
Yeah, the same with that. So I said this basically doing this. And why do I put one extra Z? Well, it's because my later computation, it will appear to be a little bit more natural. That's how it appears. So again, in reading the literature, you have to be careful that some people put Z times Z minus psi. Some people just put this as a J function. And some people, Z is equal to 1. So always be on the lookout for all these pitfalls.
What do you mean by psi here?
Sorry?
What do you mean by psi here?
Oh, psi is psi 1. Because this is only, okay, psi 1. Yeah, psi 1. And here it's really, yeah, so, yeah. In fact, here you don't even need that much. Yeah, anyway, so I won't say. The goal is to calculate small J function of projective space via localization.
What is the reason? What is the motivation to try to use it?
What's the motivation? I use J function?
Yeah.
Okay, so, well, yesterday I explained why I want to use generating. This is a different kind of generating function than this descendant generating function or primary generating function, right? So it's sort of halfway between. You have descendant in the first insertion, okay? So this big J function really calculate is a generating function of sort of a primary, mostly primary invariance plus the first point, the first mark point you have in descendants. And I could have, if I put, so this repack this information. Why? Because I can pull back from the first mark point if I pull back, this is the first mark point, I pull back from first mark point any alpha 1, okay? Then I push forward back, then push forward to a point. That will be your invariance, right? push forward to spec C will be your invariance. Okay? And so, but pull back, then push forward by projection formula, it says, well, you don't have to do anything. So that's why when, so for example, if you want to find, so this will be a vector value function, but if you pair that with any class, they'll give you invariance. Does that make sense? So this really is a generating function primary one point descendant. And I said yesterday that in Gromov Witten theory, really it's an art to find a suitable generating function for your purpose. And well, I mean, why do I want to use this generating function? There maybe, let's say, there are two primary reasons, and there are more. But the first primary reason is actually it solve this Dubrovin connection. It's the solution for Dubrovin connection. Secondly, it's easier to calculate. And I said yesterday that so the way, I mean, the only not these days there are many other ways to prove sort of this data at all count of number of rational curve in quintic threefolds. But the first proof produced by Giventhal really, I just explained how he succeeded. Well, he was able to find the correct generating function to calculate those numbers. And this was invented at that time, basically. I mean, sort of the importance, or maybe not invented, but the importance of this function was really coming out of his calculation. That, sorry? Well, I mean, as I said, who introduced, I don't know. And I will refer the question back to Professor Corti. But, I mean, he sort of emphasized the importance of this generating function because it's easier to calculate, as we will see. Because you'll see why it's easier to calculate. And because I can just do an easy localization calculation and find out what the J function is. And if I ask you to find one single invariant, it will be not easy. But to find the complete generating function turns out to be easier. It's a paradox, but this paradox often holds in Gromov Witten theory. To calculate more is easier than to calculate less. Because more, you have more structure. That's what. Anyway, so all right. So to do this, I will first tell you how I'm going to do this. Basically, so the next thing I want to do this localization is to, again, if I'm going too slow, let me know. So I will first define GD to be this strange space called graph space. And this graph space, why do I call it graph space? Well, so remember, Gromov Witten theory is basically from unparameterized P1 to your target, right? And now I want to model my Gromov Witten theory on parameterized maps. What do? There are many ways to do this. For example, you could have done is m bar 0, 3. So genetically, you have 3 mark points to parameterize. So your domain curve becomes parameterized P1. That's one way, right? This will be one way of doing that. And this is models. So this has an open subset which models the morphism, not map. Okay, of course. This morphism from P1 to PR, right? So when we say morphism space, that really mean from P1, the parameter is P1 to PR. But this one is another, where I use this degree 1 map to P1 to parameterize my domain curve. And so these two are a little bit different. In fact, you can prove this has a morphism map to that. So this one is sort of minimal in that way. And what this does here is, well, if I have domain curve has many components, it single out one component to have degree 1 in P1, right? So it has exactly one parameterized component. Does that make sense? So if domain curve is reducible, it singles out one sort of parameterized component. That is because degree 1, right? Degree 1, if you do a sort of if you want to write 1 as a partition, there's only one way. That means 1 plus 0, 0, 0, 0, etc. So one component exactly will single out for this purpose. Okay, so that is what we're going to use. Okay, so okay, unfortunately I didn't calculate this very well. I have lowered this board. So so next thing, so we want to do localization on this GD. So let me write it again. GD is the same as m bar 0, 0, no mark point, PR, P1. So in fact, let me write X instead of PR so that we will. So now I'm going to use T, it's my C star X on X cross P1 by identity. Then here you can X on so as a C star action. The natural C star action as so maybe take whatever way you like, and maybe you can think about this as Z0, Z1 being X upon by Z0, lambda Z1, for example. That will be my action. So with acting trivially on X, even though my X is projective space, I can always act on that. But I just, I choose my own action to suit my own need. That's my choice. And so now, once I have action on my target space, this by this functoriality construction of moduli functor, it acts on GD itself, on the moduli scheme. Right, or moduli stack. So this T, so induce this action, T acts on GD. So now to use localization, I have to find out what the fixed locus are. So what are the fixed loci? So let's try to find out. Well, as I said, if suppose this is your X cross P1, and P1 you have two fixed points, right? 0 and infinity, that's two fixed points by my action. On X there's no action, so it's fine. So what are the possible fixed locus of this? So I take my domain curve and map to this. What could possibly be the fixed map? Remember, fixed map means it's fixed after reparameterization of domain curve, right? So remember, isomorphism is defined allowing the reparameterization of domain curve. So what are the possible fixed map? Well, the map can map to X, but it has to map to X sort of this way. So this will be. So I'm drawing the image of my domain. So my curve will be something like this. Okay, and it will map to my target like this. So this guy has over infinity and over 0, and this will be some kind of horizontal. This will be my degree. So this guy will have degree 0, 1, and this guy will have degree D1, 0, and this guy will have degree D2, 0. Right? D2 means, D1 means map to X non-trivially, but map to P1 trivially, map to 0, etc. Is that clear? This is the only way it could have been a T fixed map. So how many components are there? Well, they are D1 plus D2 has to be equal to D, and therefore, by this two partition, we know they are They are d plus 1 components. Okay. And what are these components? Well, they're simple, right? So let's look at this. This map to P1 become trivial, and we learn our lesson. So, and in fact, it only can map to 0. So there's no choice. So what does this fixed point look like for a given D1, D2? What does the fixed locus look like? Well, you almost look like I'm going to have a map to X and map to X. So the first I have a map to X with degree D1 and map to X with degree D2. I have two maps. But then, because this is horizontal, they map to X has to coincide. So this fixed locus, each one will look more or less like this. But here I have one mark point and one mark point. This is a nodal point, but so I will write this like this. And this is not complete. So every fixed locus, every component can be, there is a map or there is a morphism from this stack to that fixed component. Does that make sense? If you just investigate what's going on with this kind of map or this kind of morphism from the C to X cross P1, what are possible fixed stable morphisms? And these are the only things. Of course, in the extreme case, I could take D1 or D2 equal to 0. Okay, so I'm going to single out one component, which is the following component. I'm going to single out so this is D1, D2 equal to D0. And if this degree is 0, that means nothing here, right? It's degenerate case. So and that space, that is the same as this M1 X D. So this guy is a fixed locus of GD. So maybe I'll write. So this guy is a fixed locus of GD I. But now I want to introduce some kind of dumb space corresponding to this. So remember, when I introduced GD, I said, well, it models parameterized morphisms from P1 to PD. Right now, I do have to use X being the projective space. So what is a general morphism from P1 to projective space? Well, this just this is the same as some kind of R plus 1 tuples of homogeneous polynomial of in two variables. In fact, these two variables will be your P1, which let's say Z0 and Z1 of degree equal to D. The space of R plus 1 tuples of homogeneous polynomial in two variable degree D1, of course, because being a projective space means you have to quotient that by C star. But I will talk about this a little bit. Does that make sense? Well, what is this? This just, describe P1 to projective space just like that, right? And of course, when does this not a morphism? When you have common factors. When you have common factors, this stops being a morphism. Or at least not morphism of degree D. Does it make sense? So if I want this to be morphism of degree D, and that would not be this. Not all of these, if they have common factor, like say Z1 minus Z0 to the power of D, then you will just map to a point. Or I mean, it really doesn't make a lot of sense at that time. So what we'll do here is to say, well, I'm going to have this GD, and which is at least birational to this. But what is this? This our plus one tuples of homogeneous polynomial in degree d in two variables. So what is this? And this is, well, it's a vector space, and quotient by this, it will be a projective space. So this guy will be a projective space, and I have R plus 1. Each homogeneous polynomial in two variable degree d has d plus 1 coefficients, right? So because projective space, does it make sense? For every entry, I have choice of d plus 1 coefficients, right? I have R plus 1 of them, and I do projectialization, like minus 1. That's all. Okay, so this I will call it PRD, so we don't have to remember what that number is. Basically, it's a dumb space. It becomes projective space. And, well, the dumber the better, because I'm going to use this dumb space to calculate. So this GD, of course, is complicated. I mean, it's at least appear to be very complicated. So this is okay, right? So this is very dumb. I'm going to cover that. And so this GD is quite complicated because it's modular space, stable maps, etc., etc. So at least we find PRD, which is birational to that. And the key statement here is that there is a morphism of this. From GD to PRD. In fact, you can describe this morphism, but to prove a morphism, it will take some work, and which I'm reluctant to do. So anyway, so basically when the domain curve is smooth, it just goes through, right? When domain curve is, so an open part is no problem. When the domain curve is stop being smooth, you have these you have this kind of thing which you have D1 which might map to a point, and so because there's one single, so what is point here? It will be some kind of, one of them will be like D0, 1, and others will be like D1, 0. Other will be D1, D2, D3, 0, etc. Domain curve will look like this. Only one of them will have 1. Okay, so this guy, these things will create these common factors. I already covered that. These things will create these common factors at this point. And this guy will give you, well, after you factor out the common factor, you'll be lower degree. So that's the best I can explain now. But anyway, so what I'm saying here is there is a morphism of U which extends the obvious birational map. Does that make sense? So once I have this morphism, well, and I look at this, I say, wait, if I can find out what this is, then I can complete this diagram like this. So now I just have to find out what the fixed locus for this PRD should be. Okay, so what is PRD? Let's write down a point in PRD, what are the fixed locus for PRD? So what are PRD? So PRD, so it's going to be something which look like F0 of Z0, Z1, F1 of Z0, Z1, FR of Z0, Z1, right? So it's R plus 1 tuples of degree D homogeneous polynomial in two variables. So each one of these can be written as maybe A0, Z0 to a D, plus A1, Z0, D minus 1, or Z1, AD, Z1 to a D. And then this one you can write again. So how can you, and since my action is to make z1 goes to lambda z1 and z0 stays z0, what are the possible fixed locus? Well, I notice that on every coefficient it acts differently. On this, I act by lambda 2 at 0. On this, I act by lambda 2 at d. Okay? So the only way it could have been fixed is that they, at every, in every entry, I will have to have the same power of lambda. So by projectivity, I just factor it out. Does that make sense? So what about possible fixed locus? Well, the fixed locus will be something like this. So fixed locus will be something like, it can only be A0, B0, C0, etc. Union, I can only take 1, all of them together. Up to AD, BD, etc. Does that make sense? I can only take the same, like here I take A0, here I will take B0, here I take C0, etc. Okay? Or A1, B1, C1. Because if you mix A0 with B1, here the lambda action will be trivial. Here the lambda action will be the first, lambda for the first power. Then you cannot factor out. That's non-trivial action. So the only time it can be fixed is this. And every single one of them, of course, is isomorphic to projective space. So guess what? The fixed locus of this, which we've just shown, that the fixed locus of that is R plus 1 copies of projective spaces. Sorry, 0 to R, maybe P. And, oh, sorry, not R plus 1, but D plus 1. Apologize, D. Right? D plus 1 copy of that. And look at that. We have D plus 1 copy here. So they're married to each other. Okay? By T equivariant map. So here, if I choose this, I will have exactly 1 map 2. Well, again, and if there is a morphism, it certainly induces a morphism here, right? And you have to think a little bit about this. But again, so to use an evasive term, once you think about it, it will be more or less obvious that this will be evaluation morphism by first mark point. What else could that be anyway? Does that make sense? So to calculate this, okay, now, I tell you so much about all these. Why does that relate it to J function at all? Why is that related to J function? Now, if I look at this formula, then I just erased my formula. Anyway, so if I look at this formula, then what I will So now I look at this formula, what I want. Now all I need to figure out is Ni and Nj. Okay, so but why is that related to J function? So let's look at what's a normal bundle for this. And so in this case, the virtual class is the same as the fundamental class. So we don't have to worry about virtual class in here. This is these are all orbifolds, smooth orbifolds. And then the virtual class is the same as functorial class. So I don't have to worry about the virtual class, etc. But let me try to figure out what the normal bundle for this is. Okay. So look, because my choice of this fixed locus tell me that my D1 is D and this is 0, right? So it's going to be this diagram. So map generically only two components, two reducible components in the domain curve which map to D0 and 0, 1. Okay, so let's try to figure out what the normal bundle is. And again, in practice, what would you do? Well, I would have to first figure out what rank of the normal bundle, what dimension of normal direction is, right? So what is the dimension of normal direction? Well, I calculate virtual dimension of this, I calculate virtual dimension of that, I find out the normal bundle has to be rank 2. So normal bundle of this. Oh, sorry, this is a bit too crowded. Rank of Ni is 2. In practice, you sort of, well, I mean, that's all I always do. You know, I first establish the fact, and then I try to explain the fact. So let's try to figure out what are the normal bundle. But what is normal bundle? Normal bundle means I will deform this fixed locus to a general point. So there are basically two directions I can deform this to a general stable map or stable morphism. He left. Great. So to a general stable map. How can I deform this? Well, there are two ways, basically. Once you think about this, there are two ways. One is because I said, look, I need to stay on 0, but generally, of course, this doesn't have to stay on 0. If I'm not asking about, in fact, I want to deform this to unfixed, right? Unfixed stable map. So I can deform this out of 0. Okay? And another way to deform it would be obvious, like I can smooth my nodes. Right? I have this node, I can smooth it out. So two directions. Does that make sense? So at rank 2, I have two directions. One is to move this vertical out of 0 in P1. So I map to 0 in P1. I don't have to map to 0 in P1. If I'm deforming out of fixed locus, right? If you map to 0, that would be fixed locus. I want to deform. Normal bundle means I'm going out of fixed locus. And the other one is like I can smooth the node. So that's exactly 2. Sound like we have a good match. And so now I just have to calculate the Euler class of that. And so what is the equivariant chain class of these two? You notice that when I move this away from this, I'm moving the point on this component, right? But on this component, it's really trivial. The moduli is trivial. This is M bar map. This is a degree 1 map to P1. So this is a trivial moduli space. So I'm giving a trivial bundle. So this direction will be trivial direction. And this direction will not be trivial because I'm smoothing the node. And as you learned in the first week, that's governed by sort of a tensor product of a tangent bundle at the node. Right? Smoothing the node will be smoothing this node. If you write this as P prime and P double prime, the smoothing node will be T prime, T double prime. That's it. But this part has no modular. P1 map to P1 of degree 1 has no modular. Therefore, this won't be trivial. But because we are talking about equivariant cohomology, right? We're not talking about usual cohomology. We have to ask whether it's equivariant trivial. In fact, it's not equivariant trivial. So this component, I'm going to erase this. This component, the first part will be exactly the first chain class of that. So this part, C1t of that, will be exactly t. If you think about it, I'm moving this away from, so it has a t-equivalent action on that. So it's topologically trivial, but group theoretically non-trivial. On the other hand, if I'm deforming this, and this part is group theoretically trivial, right? So I have to use this, right? But C1 of this will be C1 of this plus C1 of that. Okay, so the first part gives me the psi class on the first mark point on this component. So this guy is C1t, the first minus. Well, because psi class is a cotangent, so I have to use a dual of that minus. And this part, again, on the horizontal direction, it's again topologically trivial, but equivalently you have to add t. Well, actually z. Sorry, so I use z notation. So what is the no? So now we figure this out. E of ni is the same as z times z minus psi 1, and that's why I use. Well, that's good because that has been a denominator, and that very much match the J function we've been talking about. Okay, now to use that formula, what do I want to do? I want to choose choose alpha to be 1. If I choose alpha to be 1, because this is birational, 1 means fundamental class. Push forward fundamental class is exactly the fundamental class there. So that means does that make sense? So here I have pull back of 1 is 1, and push forward 1, and pull back, and so push forward, this will become 1. And again, pull back of 1 is 1, so the whole thing is also 1. So this will be 1. So use the correspondence of relative. What I have here is this. And in reality, I should put this as ET or something, T here, just to remind us these are equivalent Euler classes or top chain classes. All right? So once I have this, then look, so this is, and so restriction of mu here is exactly EV1. So I can just put this as EV1, push forward. Look, this exactly look like the component J function JD, or that component JD, right? So J function is sum of all D, and the Q to a D component this is exactly what you need to calculate. Okay, so now I transform this problem to calculate 1 over the equivalent Euler class for the normal of projective space inside a projective space. So how hard could that be? Right, so I just have to calculate the weights and calculate normal bundle of a projective space inside a projective space. And if you do the calculation, you find out this guy in that. And in fact, this embedding is very explicit, right? Remember, it's A0, B0, C0, D0, etc. So you know exactly what happens. And so you need to calculate. If you calculate normal bundle of this inside PRD, and that's exactly, so maybe I'll say ET of that. This is exactly, so for A1, you have this, H plus Z. For A2, you have H plus 2Z. A3, you have H plus 3Z, because this is what your equivariant action is. You remember, it's A0 means lambda acts trivially. That's what our fixed point. A1 means lambda acts by first degree. That's Z. So all I'm doing here is M from 1 to M from 1 to R. Right? So I'm taking A0, so I have A1, A2, A3. So that, but I have R plus 1 component. Sorry, this is to D, and I have R plus 1 components. Does that make sense? I'm afraid if you've never seen any localization, this might go a little bit too fast, but you have seen this, you'd probably be bored. So what's the point of talking about this? I don't know. Anyway, so basically what I'm saying here is I take A0, A1, and B0, B1, etc. So these A1, A2, A3, B1, B2, B3 would be my deformation direction, right? What's A1? A1 will be H plus Z. A2 will be H. The first chain class of that will be H plus 2Z, because this is a lambda square action, lambda cube action, etc. And for every lambda action, I have R plus 1 of them. Lambda square, I have R plus 1 of them, etc. And this will go to lambda to a D, which goes to AD. So that's that many directions you can deform, and that gives you the equivariant Euler class. So there you have it, the J function of that. So now the conclusion here is J function of projective space is going to be if you then you have this. Of course, here it looks like a strange thing, but really what I'm asking is I have to invert this, right? So what do I mean by this? I'm taking this J function as a power series in Z inverse. So I have to invert all these things and bring this H to a top. Then, of course, you'll go like coefficient of 1, coefficient of H plus, up to H to the R. And H to R plus 1 will be 0. So this can be written as something like this, plus. Right? Does that make sense? Because I have to say that, for example, H plus Z, I will write this as Z to a K plus 1 and H to a K, summation K. But also K go from 0 to R, because H to R plus 1 is 0 in projective space, PR. So I just invert all the terms and multiply them together and use nilpotency of H. I can write this in terms of a vector in H our stuff. So this will be Does that make sense? So it's a long calculation, but this is a technique you will learn, and in fact, you have learned it if you sit in David's talk. He actually has carried this very, very, very far away from this already. So I'm backtracking to a very, very, very elementary example. But hopefully this is useful. And then, I said that there are two things I want to talk, two techniques I want to explain. One is localization, which you just learned. One is degeneration. So if you're not exhausted yet, let's march to degeneration. And I won't be able to finish degeneration, but I won't start it. So again, or maybe you already learned this in David's talk, so I don't have to. Yeah, he used a lot of degeneration already. So if you already learned it there, then then you can go ahead and enjoy your lunch before I do mine. But if you haven't, then here is what I had to say. So to do a degeneration, you have to define the relative invariance. So I will say a little bit about relative invariance. Okay, let's change the subject. So relative Gromov Witten theory. So I'm going to change notation. I'm going to denote my variety by y, smooth projective variety by y for now. And you remember that there is this sort of stack of expanded degeneration. I can first form this L. This would be so okay. Y, and then I have E. Y is non-singular projective variety, and E is smooth divisor. And so I have, and then from E I can perform this, what I wrote as P1 is defined to be the projective bundle of normal of E in Y direct sum O. As in David's lecture. And so this guy is just like I take this and union that on E with P1 E. L of them. Okay, so the picture I'd like to have here is like, here is my Y, and this is my E. Here's my Y, and I just glue it to a. This is a P1E, P1E. L of them. Okay, so the trouble with this relative space is that to define a good moduli functor, you do have to expand this target. You have to, the target become a changing, target is keep changing. And the reason is that, the reason is simply because if you don't change your target, we won't be able to form a separated moduli stack. And so, in fact, this is a very good scheme. It just has this sort of a normal crossing singularity on all these E's, right? And so when I write YLE, I mean this E will be the last E you have. So this will be the very last E you have, because this P1 would have two E's embedded, two natural E embedded. One is, take this, 0 section or infinity section, right? You have two natural E's embedded. Does that make sense? And so I want to make sure that, so this E has normal direction NE in Y. I want to make sure this direction is N E in Y dual, and this normal direction is N E in Y, etc. So this E again will be N E in Y. So this will be your the original normal line bundle of E in Y. That tells you how I glue it. So I have two E's to glue, and I want to choose this E to be the zero section of this, which means I take the zero section of that. And this will be infinity section, zero section, infinity section, and this will be your infinity section, which has normal line bundle, and E in Y. So, okay, so what are the moduli points? So, to define a moduli, I have to fix a topological type. So I start with, I call it gamma. I have genus G, N, and beta. And mu, this mu is a little bit different from what this is. I'll tell you what this is. Well, G, so now I want to form a moduli of maps from a curve into this YL. So I want to study what the C into YL relative to E. And what are these? Well, this G is the genus of domain curve. N is the number of mark points. Beta is a class of the beta. And but you say, well, hey, but you are mapping to YL. What's the beta? So beta is that YL has a natural contraction to Y. And so beta is defined to be, so let me call this P. This is, again, a class in Y, not class in YL. Okay, because L keep changing, I don't want to specify mine. And what is mu? So, okay, so now I know my curve class is beta, so the beta intersects with my divisor to be some D, right? So it's a number. The curve and the divisor intersects, and this number is topological. So but the curve intersects this E, genetically will be D points, but it could have multiplicity. So I'm going to specify the multiplicity on that. So I'm going to choose a partition. So this mu is a partition of this. In other words, mu will be something like summation mu I from 1 to rho, where so such that summation of mu is mu 1 up to mu rho is a partition such that summation mu I 1 to rho is the same as beta dot E. So I specify a little bit more because I have a divisor and my curve does intersect with divisor. I want to specify how it meets, how the curve meets with the smooth divisor I chose. Okay? So on the surface, this kind of map will be will be a restricted map from C to Y, right? So if you don't forget about L, if there's no L, C to Y with this condition will be just saying that I only choose those maps which has exactly this kind of counter order with my divisor. Okay, so geometrically, this will be saying that I specify the counter order. This mu specifies the contact type of beta of your map with E. So the curve certainly intersect with your your divisor is a topological number. I want to specify how they interact with each other. So if on the open subset, this will be some kind of subclass of that. And if everything can be deformed to general position, so the biggest cell will be like 1, 1, 1, 1, right? The row will be exactly the same as D, and mu1 will be 1, mu2 will be 1, etc. So that's genetic. Genetically, you will imagine this intersects all transversally. This is your E, and this is your curve, or we say 1, 1, 1, 1, 1. But you can specify, hey, I just want this to be contact order 3, then 1, then 2. Well, I mean, look, this is 3. It should look like this, right? Anyway, so one, then 2, etc. So you can specify your contact order in like contact type in some way. This is like a generic case. This will be some kind of case you want to specify. So it's sort of refined Gromov Witten invariance. Does that make sense? So with this refined Gromov Witten invariance, I want to define. I want to tell you how I define this refined Gromov Witten invariance. But unfortunately, well, I mean, fortunately and unfortunately, this has to be a bit more abstract than usual Gromov Witten invariance. Namely, as you already heard from David's talk, that this will be something which I'm not really mapping to YL, but some kind of YL quotient by sort of a strange stack. Okay, so the moduli. So the moduli here, I'm going to write down Y, E, as a point which, so every moduli point will look like this. I will have a pre-stable curve mapping to 1L with mapping to Y, okay, such that, of course, this F, so when it composes with P, this lower star of C will be the same as beta, and then F upper star of E will be summation mu I yi, certain points. That means I fix the contact type of this, and such that topologically means this, and such that, and of course genus of this is going to be G, and then you have m mark points there, and etc. So, and the two new things I have to say is that this F, this satisfies something called pre-deformability condition. What does it mean? That means if I have this is my Y, and if I go like this, this is my all this, and on every singular locus, remember YL is singular, right? It's normal coordinates. It has more normal coordinate singularity. It's the double point. It's a sort of double point. Double point as it has a double point on every these E's. On every E, you have to ask your curve can go like this and that. I ask that sort of this is contact condition has happened in the way that from both sides the contact condition has to be the same. So it's written in the notes that a preimage of the locus, and so there are two things. The preimage of the node of a singular locus of YL has to be must lies on the singular locus of your curve, and then for every node P. Well, my node can map to smooth part can map to the singular part. But on the singular part, there cannot be a smooth. It had to be singular. My curve had to be map there had to have a singularity. And for every point, every node there, the two branches of C at P mapping to a different component have the same contact order. So your curve will have to map like this, and then you will have to exactly match this, etc. Does that make sense? In other words, I cannot ram my smooth curve through here. That's not allowed. And also, contact order has to. So this is very similar to what Alessandro was talking about. And that's why I call predictability condition, because you remember how this normal crossing device really formally locally look like yz equal to 0. So I want to make sure my curve also like that. So when I deform this to be smooth, my curve can be deformed to smooth. So that's why it's called predeformability condition. So that ensure that I can deform things to a smooth thing. At least heuristically, I can deform all the setting to a smooth setting. Okay, so oops, I already gone over time. So now I just have to tell you when they are isomorphic. Once I tell you when they are isomorphic, so to define a moduli stack, right? What else do I need to do? I need to tell you when I already told you like what the moduli sort of a point is, or that the objects are. I will tell you what the equivalence class of this, right? Then I basically define moduli functor. Well, I have to define for families, but I consider not define anything for families. So I won't define over point. So tomorrow I'll tell you how to define this, how to define equivalence relation. Then I'll define moduli stack. Then we can, once we have a moduli stack, we can define invariance. So I think that's all. Thank you. Oh, sorry. Sorry? Is it possible to define what? For x equal to, or sorry? Yes. Well, but then you don't have that PRD. I mean, you have to first find PRD. Whenever you have PRD, then you can more or less define that. I mean, for toric variety, so for example, she was asking whether I can change that when x is not projective space. And what I'm saying is when x is not projective space, then what is PRD? There's no PRD, right? I cannot model that on some kind of simple space. And so, but when x is toric, smooth toric varieties, then you can find some substitute for that. Oh, in general, there's no replacement. I mean, this is sort of I mean, I gave this example because so I was lucky to find this example, which is sort of easy to compute. But really, there's no replacement for general PRD. And for toric, you can define toric, some kind of toric map space. But usually, the space will have a wrong dimension. You do have to put into a sort of abstraction bundle to correct that. There's some kind of naive virtual class, and so that the map itself and then GD will not also in general not to be smooth, and so you have to find a virtual class. And in many cases, well, in all the toric cases, actually what you can do here is to replace GD by GD ver, and PRD be some kind of toric map space, and you can also define some naive virtual class, and this is no longer birational, but you can also prove it's virtually birational. Means if I take, so the mu I use the fact that mu lower star of 1 is 1 for birational morphism of smooth orbifold. But if I can, I also in that case I will be doing this virtual, the same as virtual. In that case, you can prove that. Not always prove it, but anyway. So in some cases you can do that. Other questions? Yeah.
There may be some singular point of the curve C along the singular locus of Y.
Yes.
Or there may be.
Well, we actually we more or less requiring this. So first of all, the singular locus of Y, like these, right? They're a copy of E, right? And on this E, so this is singular locus of Y. Preimage can only be a node. So on the singular locus, the preimage can only be node and nothing else. Of course, if you have node, you can also map to a smooth part. That's okay. But you know, if you want to map to a singular locus, you can only map node to that. And the reason I explained was I want to smooth this out together. So that's why I said it's a pre-deformability. I mean, it's sort of deformability condition, but I don't guarantee it's deformable. So it's a one necessary condition for deformation. I want to smooth out. If I want to smooth this normal crossing, and I also want to smooth out the curve together, and that's the condition. For example, we take Y to be a curve, E to be a point. Then you'll figure out this is really the condition you need to smooth them together, right? So